Okay. Yeah. Well, I didn't hear the bell ring, but yeah, it's about time. Okay. So today is actually the last lecture of this class for this semester. Okay. Of course, like we will still have like the final exam next week and the term project presentation the week after next. Okay, and yeah, so that's and today, okay, we are going to the material that we are going to talk about today. Part of them, okay, will be covered in the final, but you know, the other will not. Okay, because I kind of feel like some of those details are not are too much detail and require a lot of memorization, which is not what I like. Okay, so I mean, if you want to do that, I mean, use those like a concept, you can always check back. I mean, the textbook at a later time anyway. So yeah, remember we talked about the this thing. Okay, model is not the real world. Okay, all models are wrong. Okay, we are only we only want to find the model that's the best or the better. I mean, probably I shouldn't use the term best. I mean, if you have multiple models, like which one is the better one? Okay, I mean, when I say a better one, I mean like it can explain the problem, it can explain the data better. Okay, so that's like the main topic, the most important job of the model comparison. Okay, so we talked about that we could use posterior predictive check, okay, to compare models. Okay, and we saw the example like this. Okay, we have a bunch of points from a CSV file actually. Okay, and then okay, we intentionally create two models. The first one is a linear model. The second one is a polynomial model. Okay, quadratic model. Okay, the first one is called model L. The second one is called model P. Okay, P stands for the polynomial. Okay, and yeah, this type of stuff, I mean, we have been discussed those many times. So I will not go into a detail. I mean, on how to construct these two models, because these two models are really simple. Okay, but if you put them, you know, on this data points, okay, you try to visualize the result. Okay, you will find that okay, the orange one is the linear model, and the green one represent the quadratic model. Okay, keep that in mind. Okay, keep that in mind, because later on in all the figures, you will have to remember. Okay, the orange one represent linear, the green one represent the quadratic. Okay, so you can see on this figure that, you know, both model looks fine, right? Both model looks fine. I mean, they sort of explain this data pretty well, right? I mean, visually speaking. Okay, visually speaking. So so what do we do? Okay, one thing we can do is that we can plot the mean and the interquartile, okay, interquartile range for these two models, as well as the real data set. Okay, real data set. So the result turned out to be like this, which really doesn't give us any hint, okay, as to like which model is better. I mean, well, obviously they have the same mean, because remember that, okay, we actually normalize, I believe, like we centered the data set before we create a model. So that's why you see that, you know, the data as well as linear model and the quadratic model, the mean are almost all 0. Okay, this is like because this is the result of the centering the data point. Okay, however, when you check the interquartile, if you know the interquartile meaning, okay, basically, you know, the first quartile to the third quartile, okay, the third quartile, you know, this is the first quartile. This end is represent the first quartile. This end represent the third quartile. Okay, 4分位数啊，4分位数。Okay， 第一个4分位数，第三个4分位数。Okay, yeah, that's one way to see like how you know, data scattered in the model. Okay, so if you could use this result, okay, to identify which model is more resembled to the data, then it's great. It's great. I mean, we could have just used that model. Okay, we could just consider that model to be a better one. Okay, but unfortunately, I mean, for this particular example, okay, remember this one, linear model, and this one is a quadratic model. I mean, both interquartile range are similar, okay, to the interquartile range of the data points, right? I mean, at least, like, again, visually speaking, the difference is very minor, right? So what do we do? So obviously, this one doesn't help that much. Let me repeat, okay, if this one work, okay, we will just use this as a criteria to determine like which model is better, okay? But unfortunately, when this does not work, what other tool can we have? Okay, what we can do is that, okay, we can plot the dispersion of both mean and the interquartile range as opposed to their mean values. So we can sort of like, because remember, okay, when you get a model, okay, of course you also get the posterior for all the parameters of the model, right? You have the posterior, okay. It's not just like okay, a model and the sum result. No, it's a complete you know, probability distribution, okay, of all the parameters, okay. So what you can do is that, you know, because it's a distribution, you can, you know, keep, you know, extracting samples from a model, right? This one we can do that, right? For example, like we have a model, okay. We try to use the posterior predictive check, okay. We can, if we call that once, we can extract some sample from the model, okay. But you can call it function multiple times, and as a result, okay, you can see like what we meant by the dispersion of mean and the dispersion of the interquartile range. Okay, I mean, for model we can do that because model, I mean, represent certain distribution. Okay, certain distribution. I mean, it's a posterior distribution, but the most important thing is we can you know, we can obtain the samples from this you know, distribution. Okay, so here's the thing. Okay, we can draw this figure. This will be a more interesting figure, okay? This shows, you know, the dispersion, or I should say distribution of a number of samples you obtained from the posterior distributions. Okay, because each time you get some sample from the distribution, you get a mean, right? You get a mean. So you can do this multiple times, and that represents the dispersion, okay, or like distribution of the mean. So again, the orange one represent the linear model, and the green one represent the quadratic model. Okay, so let's not look at this one first. Let's look at this figure. Okay, and the center one, this 0.0, what is this? Okay, that's like the mean of your data point. The mean of the data point, because you only have, you know, a fixed set of data points, right? The data point is not a distribution. Okay, the data points are not a distribution. So you cannot like you know, do the mean and get of the data point and get a different value. That's impossible. So you can only get one mean from your data. Okay, which is depicted here. Okay, so you have only one value for that, but for the two different models, because what we have are the posterior distribution, so we could, you know, do this multiple times, and we can draw this figure. Okay, so of course, what we want is that this distribution, okay, the distribution of the mean should be, you know, centered at the 0.0 as much as possible, because after all, okay, the true mean is 0, right? So let's like so let's have a look. You will see like you know, yeah, I mean, let's not look at this one. Okay, let's you will see like both distributions look like they also centered at the 0, right? Pretty well. So again, this may not be a good indication. May not good, at least like a left-hand side. Okay, the difference of two models is very tiny. It's very minor. Okay, so how about let's look at the interquartile range. Again, because the data points are fixed, so we only have one interquartile range value. Okay, that's a fixed one. That's a fixed one. Okay, so that range, okay, the range basically is just like a third interquartile minus subtract the first interquartile. Okay, that will be a value for that. Or put it another way, it's like this value subtract that value. That's the interquartile range, right? So we only have one value for the data points, okay? But how about these two models? Okay, because we can sample many times and draw the distribution of the interquartile range for each set of samples. Okay, so it turns out that, okay, when you draw draw the lines for these two models, okay, the orange one looks like this, and the green one is a quadratic model, looks like that. Obviously, okay, both models are not centered to the true interquartile range that well, right? There's a small bias here, but obviously, okay, the orange model, the linear model, has a smaller, or I should say like the linear model, the orange one, is closer. The center of the linear, the distribution of the linear model is closer to the true interquartile range, right? The center of the orange line is closer to a true interquartile range than the quadratic one, right? So this, okay, is a deal breaker. Okay, we could use that to determine which model is better. Okay, which model is better. So then let's look at this p-value. Okay, this p-value. Okay, what does this p-value stand for? I mean, this p-value, the definition is very, very similar to what appear in the traditional or frequentist statistics. Okay, let me first tell you the meaning of this. How to use this p-value. I mean, by the way, when we say the p-value here, what we are talking about, okay, although the name looks the same, but this p-value that we are talking about, I mean, this is actually the Bayesian's p-value. Bayesian p-value, okay, as opposed to the traditional, p-value in frequentist version. Okay, so even though the definition looks similar, very similar, but they are different. I will explain the difference, in a minute. But now let me explain. Okay, how do we use them? Okay, use this p-value. Okay, if the data and the simulation agrees, okay, we should expect this p-value around 0.5. Okay, so this is a good indication. It's a good indication to tell us, like, whether or not your distribution is centered at the right value. Okay, I mean, in this particular example, that right value is the true data, okay, obtained from the true data. Either it's a mean or it's an interquartile range. Okay? So if it's not, if it's deviate, if the Bayesian p-value deviate from 0.5, okay, then we are in the presence of biased posterior predictive distribution. So, okay, I mean, if you look at the p-value, you will see, okay, the first one, the linear model has a p-value 0.5 for the mean, and the quadratic model has a p-value 0.51 for the mean. The difference is very minor, just like what appeared in the figure. Okay, but on the right hand side, okay, for the interquartile, okay, the p-value for the linear model is 0.37. It shows a little bit bias, right? But for the quadratic model, the p-value is 0.23. It's even worse. So if you want to use, you want to justify which model is better numerically, okay, quantitatively, okay, then this Bayesian's p-value could be a good one to use, okay, along with the posterior predictive check. Okay, so now let's look into what this p-value stands for. Okay, so the p-value its definition, okay, is okay the probability of like your simulation result. Okay, this T stands for any index. Any index. It could be mean. It could be interquartile. It could be, any other, summarized statistics stuff, such as like the standard deviation, or anything you can compute from a distribution, or from from your data, basically. Okay, as long as it's a one value. Okay, so it's a probability of the index you compute from simulation is greater or equal to the probability of the observed. This observed is the true data. Okay. Given y is the data. Okay. So in the examples that we have seen, okay, the T, okay, has been used for mean and the interquartile range. Okay, and okay, you may wonder, like because like earlier, okay, when we talk about the Bayesian data analysis, okay, I keep telling you guys that, well, the frequentist statisticians, their work, okay, are not that. I should say there's some issues. Okay, of course they will argue differently, but I would say from the Bayesian's perspective, okay, the frequentist, biggest problem for frequentists is that they use p-value and they use null hypothesis, test. Okay, so you see, how come? I mean, we are using we are also using the p-value here. I mean, so what's the difference? What's the difference? Okay. Actually, let me tell you this. Okay, just by looking at this definition. Okay, this definition, okay, of the p-value is pretty much similar to the definition of the p-value used by frequentists. Okay, by the traditional statistics. Okay, they are similar. So what's the difference? The difference is that for frequentists, okay, the way they calculate this thing, they draw samples. When they draw sample from the true distribution. Okay, for example, like when they remember what I told you, like I don't know if you guys remember. Okay, but anyway, okay, when the issue with the p-value for frequentists is that when they try to calculate this p-value, okay, the way they draw samples from the true distribution will affect the computation of the p-value. For example, like at that time, I believe I was using like the coin flips. Okay, so for example, like so now it's the data is like this. We have like okay, we have collected 10 coin flips, and we have 3 heads and 7 tails. Okay, so I want you to compute the p-value from this data set, from this data, and you say, okay, so good, but in order to calculate the p-value, okay, for frequentists, I need to know how these data are collected. Why? Because let me give you two scenarios. Okay, the first scenario is that, okay, I just don't care, the result. Okay, I just throw 10 times coin flip and collect the data. It's like that, right? 3 heads, 7 tail, right? So regardless, the result, I just throw the coin 10 times. Okay, so the stopping criteria for my data collection is throw the coin 10 times. Okay, and then you can easily compute. I mean, you guys have taken like a probability class from high school, so based on that, you can compute. Okay, for 10 coin flips, the probability of getting 3 heads, 7 tails, right? Everybody can do that, right? That's not a difficult question to ask, right? Okay, so, but if I give you a second scenario, okay, this time, okay, the data collection is done like this. I flip the coins until I get 3 heads. I flip the coin until I get 3 heads. And it happens that, well, I throw 10 times, and the 10th time I get a head, the 3rd head. Okay? And the previous 9 times I get, well, 7 tail and there's 2 heads. Right? That's also one way to collect data, right? Right? That's also one way to result in 3 heads, 7 tails, right? But the probability of getting 3 heads, 7 tails will be very different, right? Will be different, right? I mean, if you know how to calculate the probability, right? So because of that, you can see, okay, how data is collected will have the impact to the probability distribution. Okay, and as a result, okay, it has impact to the p-value for the traditional frequentist. Okay, so that's why, as I say, if you want the frequentist to compute the p-value, that guy will ask you, okay, back, how do you calculate your data? Because without knowing that, he doesn't know how to calculate it. Okay. However, in a data science, point of view, okay, a lot of time, okay, when you get a data set from maybe internet, you have no way of knowing how the data is collected, right? You have no way of knowing that. Okay, so that makes frequentist approach problematic, to say the least. Okay, because there will be obviously certain issue when they calculate the p-value, because they have to assume how the data was collected, but it could be different. It could be different. It could be wrong. Okay. But so how about the Bayesian's p-value? The Bayesian's p-value were calculated directly from the posterior distribution. Okay, because it's drawn directly from the posterior distribution, which obviously, like a frequentist, do not have access to the posterior distribution. Okay. Okay. So, because the Bayesian's p-value, the difference is that for example, okay, remember what I told you? Okay, I say, okay, for this mean, for example, okay, we actually get like a multiple set of samples from the posterior in order to calculate this dispersion, right? But this can be done by Bayesian data analysis, but this is not available by the frequentist. Okay, and also when we do the data analysis, okay, when Bayesian data analysis is done, okay, if you check the steps of Bayesian data analysis, what is important is the prior, the likelihood, right? We don't care, we don't assume particular data collection. Okay? So that's why the result of this p-value is independent, okay, from how the data is collected. There are other issues. I'm just trying to tell you, okay, based on one most obvious problem of the traditional frequentist p-value. There are other issues as well. Okay, but I will not go into the detail of that. Okay, after all, you guys probably do not know much about the frequentist p-value. That you probably just know a little bit. Okay, so same thing. Okay, for the null hypothesis standardized test. Okay, because they are built. Okay, p-value, NHST, they are built on the same ground. So both are flow, to say the least. Okay, I mean from the Bayesian perspective, of course. Okay, so here, okay, I just want you guys to understand. Okay, the Bayesian p-value could be used as an indicator. Okay, to identify which model is better. Okay, so this is like what this is, and this is this is what we call Bayesian p-value, and also why it is different from the frequentist p-value. Okay, you need to understand this. Okay, things like this. Okay, by the way, could appear in the final exam. Okay, obviously, because final exam is next week, right? Okay, so I mean the way I give the questions in the final exam, I always give like a big concept type of problems. Okay, for example, this is one of the important concepts. Okay, what's the difference between like a Bayesian's p-value and frequentist p-value? Okay, and how do we use the p-value? Okay, in Bayesian data analysis. Okay, so I think I already discussed that. Okay, so posterior predictive check. Okay, either we use plots or numerical summaries. For example, like a Bayesian's p-value. Okay, either combination of both. Okay, very flexible ideas. Okay, they are flexible idea for the model comparison. Okay, so this concept is general enough. Okay, to let us like come up different ways to explore posterior predictive distribution and use whatever fits to tell a data-driven story. Okay, including but not restricted to model comparison. But of course, in this chapter, we are primarily focused on the model comparison. So in the following material, we are going to explore other methods, okay, to compare models. So the first tool that we can use is posterior predictive check. The second type of tool, okay, it has a big set of stuff. that we are going to talk about. I mean, but there are some principles that I would like to, sort of like inform you guys, okay, before we go into detail of like different tools, okay. So when choosing among different models, okay, there's an important guideline, okay, known as I think this is called ACME, okay, Archimedes razor, okay. I don't know how this name is obtained, okay, because razor normally is you know, for shaving the beard, you know, something. But obviously this is not the way of this word. I mean, explained here, okay. Basically, okay, this Archimedes razor, okay, state something like this, okay. If we have two or more equivalent explanations for the same phenomenon, okay, if you have more than, two or more than two explanations for the same phenomenon, then we should choose the simpler one. The simpler explanation for a phenomenon is preferred. It's preferred. Okay. Second, given simpler models, okay, are easier to understand than more complex models, we should keep the simpler one. So simpler models are preferred over complex models. Okay, so the first statement tells you simpler explanation is preferred over the the complex explanation if they have the same, if they are sort of have the same explanation, ability to a certain phenomenon. Of course, this is the assumption. Okay, if they are roughly have the same expressive power to a phenomenon, then you should choose the simpler one. The second one tells you, okay, if two models performs roughly the same, okay, then you should pick the simpler one. So by the way, if we apply the Occam's razor, when we are at this figure, we actually can already have a conclusion. Why? Because linear model is simpler than the quadratic one, right? Linear model is simpler than the quadratic one. So, well, I mean, because they roughly have the same expressive power, they roughly can explain your data point about at about the same level. So we should pick the simpler one. So you can pick the linear model here, right? Which happened that, okay, you can see, well, the simpler one is better. Okay, when you have a more complex analysis that actually fit like that's like happen to be the same as like what Occam's razor suggested. Okay. But anyway, this principle is very important. Okay, another justification is based on Bayesian statistics. For example, like a Bayesian factor. Yeah, we are going to talk about Bayesian factor, but we may. I think at some point I have to draw a line, okay, to stop, because like there are a lot of like material that are pretty dry, okay, from in between. I mean, before we cover the Bayes factors. So I will try to cover Bayes factor, but I will tell you, you know, where the final exam will, you know, will be covered. Okay, I mean, but not the base factor. Okay. So another factor that we take into account for model comparison is accuracy. Okay, so how well the model fits the data. Okay, basically. Okay, so in the previous chapter, we already used like a, you know, coefficient of determination R squared. Okay, which basically explain like the accuracy in certain, you know, it sort of explain the accuracy. So we want the model with higher accuracy. So you know, the R squared value, okay, is one of the such indicators. Okay, if you already forget what R squared is, I mean, remember I show you many figures that has like different R squared values. Okay, for x and y, okay, the correlation between x and y. Okay, if you don't remember that, I mean, check. I think like last chapter or the chapter before last. I forgot, but yeah, we talked about this. So intuitively, it seems that when compare model, we tend to like those that have high accuracy and those that are simple. But here, okay, this you know, so we have two criteria here. One is accurate, one is simple. Okay, but these two may not coexist. These two may not coexist. Okay, so what should we do if the simpler model has the worst accuracy? Or more generally, how can we balance both contributions? Actually, as I said, like normally simpler model tend to have you know, lower accuracy. Okay, or let me put it another way. Okay, the model, okay, will become more and more accurate when you increase its complexity. But up to a point, when you increase the complexity, the model's accuracy no longer will no longer be it will be actually so it's something like this. If this x-axis represents the complexity of model. Okay, of course the larger the x value, okay, the more complicated the model is. The y represents the accuracy. Okay, again, the higher the y, the more accurate it is. Okay, what you normally see is like this. Okay, so there's like a sweet spot that we want. Okay, if we are here, we have some issue. We call this thing as underfitting. If we are here, we call this issue as overfitting. Okay, so this is it turned out to be a very, very important concept in machine learning. Okay, in machine learning. Okay, so how do we balance the accuracy and complexity? Okay, so we are going to discuss this idea, okay, of balancing between the two contributions, the accuracy and simplicity. Okay, so this topic is more theoretical than the previous one. Okay, but we are not going to get into the mathematics part of that. Okay, we are going to use just like code, figures, examples. Okay, to help us understand. Okay, this intuition. Okay, of balancing these two things. Okay, so we are going to begin by fitting increasingly complex polynomials to a very simple data set. Okay, so here we go. Here we have like 1, 2, 3, 4, 5, 6. We have 6 points. Okay, 6 pair of x, y values. Okay, so this is a very, very simple data set. Okay, and here, okay, we try to create, I believe, like 4 models. Okay, we create 4 models. So in this figure, okay, you see this point, this point, this point, this point, this point, this point. We have these 6 points, right? And then you can see that, okay, we create 4 models. The first one model, the order is 0. R squared value is 0.0. Remember, R squared represent the accuracy, right? R squared represent the accuracy. The higher the R squared, the more accurate your model is. Okay, so order 0 obviously has a very bad accuracy. Okay, so order 1 is that linear model. Okay, which gives us that. Oh, by the way, order 0 is that orange one. Okay, because order 0 basically just a constant. Okay, that constant is represented by this orange line. Okay, and that orange line actually will be, okay, if you try to use such a model, okay, to feed the data, what you are going to get is the average of the data. Okay, or put it another way, the average of the y. Okay, that's very intuitive, very natural, right? Obviously. Okay, and order 1 represents the linear model. Okay, we talk about linear regression all the time. So the green line represents that linear regression result. Okay, and order 2 is like a quadratic model. So it's represented by the I believe it's a red line, and order 5 represent. I mean, is we have like if you try to write down a model with order 5, you will see that you have actually 6 unknowns, right? 6 unknowns, and obviously, if you try to fit a model with order 5 to 6 data points, you get a perfect fitting, right? You get perfect fitting. So that brown line gives you a perfect fitting of those 6 points. So and you get R squared to be 1. It shows you that the accuracy is perfect. It's perfect. So you say like, well, how come we don't see a drop down here? Okay, I will explain this shortly. Okay, because we are using, I mean, here the R squared is calculated. We use training data set to calculate. In that case, yeah, I mean, the R squared will keep increasing as long as you increase the complexity of the model. Okay, but and also you see like when order change from 1 to 2, you can see the R squared value also increase, right? But obviously, the increase of R squared, is much more dramatic from, between order 0 and order 1. Then the order 1 and the order 2, right? Okay. So R squared value, when you increase from 2 to 5, the only difference is 0.02. There's not much difference in terms of accuracy improvement. Okay. So obviously there's still a sweet spot here. Okay. The improvement obviously is much better for order 1. And also, when you look at this data point, you can obviously see that this data point, okay, if you are going to have more data points, most likely those data points will appear somewhere near this line, right? So you can probably tell that, okay, just by this visual result, that, okay, either the linear model or quadratic model will perform better when you have more data points. Or put it another way, when you predict the other values, okay, because obviously you train the model based on certain data set, but eventually this data set is going to be used for prediction, right? Which will be used, okay, this means you are using this model for the data points that are not seen in a test data set, right? In a training data set, right? So obviously, okay, just by the visual result, you can probably tell the model of order 1, order 2 will perform much better, okay, for the future data points. For the future data point, but we are going to, talk about this in more, numerical manner. Okay, let's take 10 minutes break. When we come back, we'll continue. Okay.